Okay, recording has been already started. Okay, let's start the lecture. Great, I hope you are well and you are having a great week. So today we are going to discuss, actually we are going to make an introduction to modeling, and we will continue to discuss this topic next week, both in the workshop and in the next lecture. And let's look at the agenda for today. In the past 2 weeks, we were discussing data understanding, data preparation, and now we are at the one of the most important stages of Christian methodology, which is modeling. Today, we are going to make an introduction, but still, we will discuss some of the steps from data preparation. Modeling stage is directly related to data preparation, and the things today we are going to cover also relevant for data preparation part. If we look at the learning objectives at the end of this lecture, you will have an understanding of what are the different modeling types and what's the purpose of these different modeling types. And our main focus would be on identifying informative attributes, which is also known as feature selection, and it's really critical for machine learning models. So we will focus on that. And then if we have time, we will start by discussing decision trees. It will be actually directly relevant to the informative feature selection today. We will start to discuss decision trees, but I'm not sure whether we will have enough time. So we may cover the third part in our workshop next week. Okay. So we can actually divide the models, or in general, modeling in two groups, predictive models and descriptive models. Predictive models we were actually discussing in the past few weeks. And let me also activate, sorry, what happened? Yeah, let me activate my pen. So in the predictive models, we are trying to identify a value of interest. So this might be house prices, stock prices, or whether a transaction is fraudulent or not, or whether customer is going to leave or stay. So we have one particular outcome that we would like to predict. If it is a regression type of case, like numeric outcome, like house prices, or it might be classification, as we were discussing in the past few weeks, like predicting churn, predicting whether a transaction is fraudulent or not. So in both cases, in predictive modeling, we have a particular outcome, and we call this outcome target variable, and our main aim is to identify this target variable. Descriptive models, on the other hand, they don't have a target variable, they don't have a value of interest to predict. They try to bring explanation to the data set. So we try to understand the relation between different features in the data. The most well-known example from the customer segmentation, marketing, we have customer data, and we try to understand which features of the customer are actually affect each other, and whether by using this we can come up with a segmentation. So in predictive models, we have a value of interest target variable. In descriptive models, our main focus is to explain the data itself. So let's discuss this over an example. Predictive modeling is also known as supervised learning. The reason is that when we provide the data to a machine learning model, we provide the target variable, and we also provide the independent features. So when we decide the value of the target variable, we use features, and actually model learns this relation. So it is supervised learning. Model already know the value of the target variable, and the main focus is to understand how these independent features the target value, so that we can use this to predict the outcome. So as an example, let's say we have an advertisement case. We are allocating some budget to different advertisement channels like TV, radio, newspaper, and we observe the outcome in terms of sales. So when we allocate 500K to TV, 100K to radio, 75K to newspaper, we observe 5,000 sales. When we allocate different budgets to the channels, we observe 6,500. So our historical data keep all of these information, and model learns what is the sale amount, and at that stage how much budget we allocated to each channel. And when we receive a budget allocation plan, let's say for the future, let's say we are allocating 300K to TV, 70K to radio, 50K to newspaper, the model is going to predict what would be the sales. Okay, so this is the future target. But during the learning process, it learns between the relation of the outcome that we would like to predict, which is target variable, and the independent features. That's the reason we call it supervised learning. In descriptive models, on the other hand, this is called unsupervised learning. We don't have an outcome to predict. So model only receives the historical data, let's say about the customers. There is no particular outcome these data set actually leads to. And we try to learn between the relations of different features. Let's say we have customer database case. This is a retailing example. And for each customer in our database, we know how much they are spending for the discount and how much they spend for the monthly shopping and what they purchase most. So we keep all of these customer, let's say, transaction data, and then let's say we mark each customer as X1, X2, and so on, and then this model actually returns different customer groups. Maybe the first group is discount shoppers. This is maybe buy mostly food products, and this is maybe more, let's say, quality sensitive customers. So you try to segment your customer groups based on different features in the data set. So our overall aim is to see how these features lead to different customer segments. And when a new customer arrives in the future, when we observe how much they are spending to shopping, on discount, how much they spend monthly, and what they purchase most, we are trying to identify located so that we can maybe organize targeted promotions or advertisements to these customers. So in terms of modeling objectives, predictive models can be divided into two: classification models and regression models. So we discuss classification cases most of the time in the past workshops, like predicting whether customer is going to leave or stay, or whether a transaction is fraudulent or not, or for instance, a patient has cancer or not. So we try to classify the outcome. So in here we have categorical target value. So our main aim is to identify for the future, let's say, future customers in which category they are in. So we have a categorical outcome. This is called classification. On the regression, on the other hand, we have numeric outcome, like house prices, stock prices. We are trying to estimate a value. Descriptive models, on the other hand, can be divided to clustering and association models. And for the clustering, we are discussing this customer segmentation. We are trying to identify different clusters, different groups in the data. That is our main aim. On the other hand, in association models, we are trying to identify the interesting relationship between features. And this is widely used for instance, market basket analysis by the supermarkets, which products actually purchase together. And there's an example in here, like 70% of the people who buy spaghetti and cheese also buy tomato sauce. So which two products are most related, so that supermarkets organize their shelves accordingly. This is also widely used for web page design, how you should design your web page so that customers have more click-through. So how the features are actually related in the data. So we are going to mainly focus on predictive models and spatial classification, and business statistics you will cover regression cases. Okay, so before we start modeling, describing the modeling stage, we need to decide which variables are more informative for the model. So model is going to learn from the data, and if we give an example from churn prediction, again, and in the churn prediction, we have this customer information. If this is a telecommunication company, their internet usage, their, let's say, calls, And you can have information about the customer itself, where they live, how much they are earning, and whether they have a house or not. So this data set is quite big, let's say, and you are going to use this to identify whether the customer has a risk of leaving or not. So if you use this data completely, and if this includes every possible variable, let's say, it might seem safe, but actually it may confuse the model. So if there are lots of features available in the data set, models may not perform well. And the main idea of informative attributes, identifying informative attributes, is to decide which ones provide more information about the target variable. So which ones are more relevant for churn prediction. This is called feature selection or informative attribute selection. And there are lots of benefits of this method or technique. First of all, if we include the informative variables on it, so I'm not discussing the observations, these are the columns in our dataset, the features. If we include informative attributes, first of all, we can increase the performance of the model. So accuracy, predictions are going to improve. And also, when you identify which features are most relevant for churn, you can actually get some insights for the business problem itself. So if you know, for instance, internet usage provides lots of information about churn behavior, then this can give a company, okay, they need to focus on maybe their data packages, so it can help them to keep those customers. It can provide lots of business insights. It improves the interpretability of the model. So what does it mean? In these data sets, we may have hundreds of features. And when the model makes a decision whether customer is going to leave or stay, then interpreting that result based on, let's say, 100 features is not easy. So it might be complicated. But if you have only informative attributes, not 100 features, but let's say if you have only 50 or less than 50, then you can understand what this churn decision is based on. So it can increase models' interpretability. And it can reduce the dimensionality. So we are going to only use informative attributes when we are making prediction. So in this case, model can work much more, let's say, computationally efficient. And also it can increase its accuracy since we are actually eliminating the irrelevant features from our data. Okay. So what this feature selection is? Let's discuss it over an example. Here we have a data set, and in this data set, our target variable is showing whether a medicine used on a patient is effective or not. And as features, we have, first of all, patient record. So what is the ID of the patient or record no, gender of the patient, age of the patient, and how is the condition, health condition of the patient. P is used for poor and G is used for good. So these are independent features. Here, and we have target variable to predict. First of all, we discussed that record no doesn't provide any information, right? It's like customer ID, we assign it, it doesn't have any information about the customer itself, so we can actually remove it. First of all, we remove it from the dataset. This is actually one type of feature selection. We exclude that. Then let's check the rest. We have gender, age, health. And let's focus on gender. If we know the gender of the patient, let's say if this patient is female, what can we say about the medicine, whether it will be effective or not? So can you, okay, let me quickly check the chat. Can you say whether the medicine is effective or not? What do you think? If you know the gender of the patient. Only you know the gender, you don't know the rest. if a patient arrives and you observe the patient and you know that that patient is female, can we say whether this medicine would be effective or not? We can't say it, right? So I see the answers, mostly no, that's correct. There's 50% chance. There's 50% chance this medicine would be effective if we know the gender as female. Okay. How about if we know the health? This patient has a good health. Can we say whether the medicine would be effective or not in this case? Consider individually. Do not consider combination of the features. We consider each feature individually. I see some mixed answers, like we can say yes, given this data, or some of you say that we need to consider other potential issues or other potential variables. So if we know the health as good, as you see in here, in our data set, there are 8 patients. 2 of them have good health, and in both of them, the medicine was effective. And 6 of them has poor health, and that leads to a different outcome. So although here good health shows we have a yes outcome, yes effective cases, we only have 2 samples out of 8. So this example itself is quite small, but let's say you have 1,000 patients and only few of them have good health, and that leads to yes outcome. So we can't generalize the result. If we have only few records with a particular, let's say, category in here in the health good cases, we can't generalize it. There's a danger in the future. A patient with good health may have an effective no case. When we select informative attributes, as we did here, we need to check first how they have an impact on the outcome, and also whether we have a good size of examples. If it is only few cases which leads to a particular outcome in the target variable, there is a risk of overestimating. Okay? So this is basically how we are going to select the features. We are going to check how they have an effect on the variable. We will also check whether we have good amount of data in terms of size when we make this prediction, whether we can generalize it. Okay. So there are lots of different techniques used to identify important features. One of them is information gain. This is widely used by decision trees, and actually it explains the logic of decision trees, how decision trees work when they make a prediction. Therefore, we will cover this particular technique, but I will show you some other techniques available to identify those informative features, and we will also discuss advantages and disadvantages mainly in the workshop. So information gain is from information theory, and it basically measures how much information a feature provides for the target variable, for a particular class of the target variable. As you see in here, so let me have my pen. We consider attributes individually, okay? Do not consider any combination. When we discuss age, we will only focus on the relation between age and target variable. So remember, this is our target, and this is independent feature. So can we classify by knowing the age group of the patient, whether the medicine would be effective or not? That is what we are going to measure with the information gain. And in order to calculate the information gain provided by each independent feature, we are going to use entropy. This is a concept from information theory itself. It basically measures the impurity or disorder in a set of observations. So it may not mean anything, but let's discuss it over this example. So when we calculate the entropy, we will mainly focus on the target variable, okay? And we will check how we mix the outcome of the target variable. If we have a data set with only yes class, as you see in here, we have only yes cases. We don't have any medicine effective no. All outputs are the same. That means entropy is 0. There is no disorder here. So it's pure class. So it is pure outcome. Okay. If the outcome in the target column is only one particular category, entropy is 0. We have a pure outcome. If we have a data set with 50% yes, 50% no, or maybe you can have multiple classes, like maybe you have yes, no, or in between, or maybe we are classifying according to blood types. So we have multiple outcomes. So if we have equal amount from each, this is highly disordered and entropy is 1. Highly disordered or impure. Okay. So if we have only one particular outcome, it is pure. That means when we make a prediction, we would be sure, for sure, medicine would be always effective. But if we have mix, so if we have equal amount from each classes or from each categories in the target variable, entropy is 1, and this is highly disordered or impure. Okay. So these are the boundary conditions, or let's say specific values of entropy. And this value is always between 0 and 1. 1 is disordered and 0 is pure. Okay. So we are going to discuss it over the example. In order to kind of show you, I use this color coding. This will help us to understand it better. So reds are the no. So as you see, medicine not effective, always colored red points. And yes are colored with green points. Okay. And we are focusing on gender, age, and health, but we are going to discuss each feature individually. Let's start with age. And in the age feature, we have two categories. We have age less than or equal to 30, and we have age greater than 30. So we can divide whole records. Overall, remember, we have here 8 records. And in the age category, we have two types of patients, with age less than or equal to 30 and with age greater than 30. Now here we have our two groups. In one group, we have age greater than 30, and the other group, we have age less than or equal to 30. So considering the entropy discussion, what can we say? If we know patient has an age greater than 30, for this group, is the entropy value? Can you estimate the entropy value? Can you tell me? Oh, let me check the chat. Okay. So this is completely pure, right? We have only green yes cases. So this is perfect. It's pure. So that means entropy is 0, the lowest value. How about age less than or equal to 30? So we can't estimate it directly, but it is quite close to kind of 50%, right? From one group, we have 3 divided by 5. From the other group, we have 2 divided by 5. So it is quite close to 1. We can't estimate it. I will show you the formulation. Without formulation, for this case, we can't directly measure it, but we know that it is very, very close to 1. It's quite high. Good. So I see you have a better understanding of the concept. So this is the formulation. Don't be scared about the formulation. It has a very, very easy meaning. So let me discuss it. First of all, I is, let me just have it here. Pi is the probability of class I. That means proportion of class I in the data set. So we will always focus on the target variable. Here, how many no cases we have? 1, 2, 3, and 5 yes cases. So probability yes is how many yes cases we have over all examples. Probability no, how many no cases we have over all examples. Okay, so C is the class. Here we have 2, so therefore it is equal to 2. If you have 3 categories, C would be equal to 3. So this is the amount of categories in the target variable. Since this concept comes from information theory, this is logarithm 2 base, so this doesn't actually relevant to the number of classes we have. This is due to the information theory concept. And Pi is basically the probability. In the original data set, we have 5 yes cases. Therefore, probability yes is 5 over 8. We have 3 no cases. Probability no is 3 over 8. This is the entropy of the entire data. In the previous one, we divided based on the age, but currently we start by discussing the entropy of the whole data set. When we put this down into the formulation, entropy of the whole data set, 0.95. So what does it mean? If we don't have any information about the patients, as in the entire data set, let's say we only have the target variable, without using any feature, the entropy is very high, so our data set is very, very mixed, highly mixed data. And with the information gain, we actually compare the entire entropy of the data set and how much we can decrease it by using the features. So parent here is the entire data set minus child are the actually obtained by the features in the data. And we will check how much each feature in our data set can help us to decrease the impurity of the entire data, so that when we make a prediction, we will make better predictions and our predictions will be solid. So let's start with age. We were discussing in the previous case, we have 2 categories of age and each of them are called child. Okay, so it's better to kind of discuss it over categorical features first, and then I will discuss how we actually use this for the numeric features as well. So in the age column, we have categories less than or equal to 30 and greater than 30. So let's remember our data set here. As you see, age is already a categorical variable, less than 30, less than or equal to 30, greater than 30. So in age, we have 2 categories, and according to these 2 categories, we divide our data, and these are called child. So in child 1, where age less than or equal to 30, we have 5 observations. You check how many cases we have. Overall, we have 5. I just marked them. And out of 5 examples, 2 of them are yes, 3 of them are no cases. In the other category, child 2, where age is greater than 30, we have 3 examples, 3 cases. I also marked them here, and all of them are green. So how do we calculate how much age can help us to decrease the entropy? In the overall data set, we have yes cases 5 over 8, right? We have 1, 2, 3, 4, 5 green dots, 5 over 8 yes cases, and we have 3 red dots, 3 over 8. And we have already calculated the entropy of the entire data. If I go back to the slides, here we calculated the entire data set entropy. And now we will check by knowing how many records we have in each child and how the distribution in terms of target variable in these child nodes, we can actually describe how much age can help us to decrease the entropy. Okay. So if we check the steps, how we do it, we first calculate the entropy of the entire data set, which we already did, 0.95. without using any features, only checking the target distribution. We calculate the entropy, and then for each feature, we do it separately. We start with any feature. Since it's an independent operation, it doesn't have any impact on the order of the features. We do it individually. Let's say we start with age, then we split the data according to the categories in age, and then we calculate the entropy of each group. So if I go back, we are going to calculate the entropy of this group, child 1, and we are going to calculate the entropy of the second group, child 2. You already know here entropy is 0. For this one, we use the formulation. And then when we know the entropy of each child, then we can calculate the information gain. Okay, so let's do this. But let me first check whether you have any questions before going to the calculations. Okay, so there's one question: what does minus sign signifies in the entropy calculation? You are asking the minus sign in front of the entropy. So this value, due to the logarithm, will be negative, and this minus sign will only make it positive. So that when we check the difference between the actual entropy and the entropy obtained with the attribute information, we can calculate the positive information gain. That's just for obtain positive outcome. Any questions? Any other questions? Okay, currently I can't see, but I think after we continue with the calculation, you will have a better understanding and more questions coming up. Okay, so let's start with age less than or equal to 30. When we are calculating the entropy of a particular feature, we need to first check how that feature divides the data set. So based on the categories of the age, we can actually divide the data set. And in child 1, we have patients with age less than or equal to 30. And in these patients, we have 2 yes cases, 3 no cases. So when we calculate the entropy, now it will be actually calculated based on this group. If we write down the formulation, how many yes cases we have? 2. Times logarithm 2, 2 over 5. Plus, we have 3 no cases, 3 over 5 times logarithm 2, 3 over 5. When we make this calculation, entropy is 0.97, which is what we expect, right? Here we have almost impure, totally impure distribution. Here we have slightly majority in the no cases, but this is almost half-half. And entropy is between 0 and 1. 1 means it's highly disordered. And here we have highly disordered set. It is very, very close to 1. If we calculate the entropy of child 2, we only have yes cases. Therefore, 1 times logarithm 2, 1, probability is yes. The outcome is only yes, 3 divided by 3. No is 0. Therefore, here we have 0. And entropy is 0, which we already discussed. When we have pure outcome, entropy is 0. When we have highly disordered, entropy is close to 1. And this is almost, actually, we are at the boundary. So we calculated the entropies of each subgroup in the age category. We know the entropy of the entire data set. Now we are going to calculate the information gain. So information gain, as you see in here, how much knowing the feature, so if we know the age of the patients, how much our predictions are going to improve compared to the knowing nothing. So 0.95, this is no feature case. We don't use any feature. In the no feature case, entropy is 0.95 minus. So how much we can actually decrease it based on age information. For less than or equal to 30, what is the proportion of the cases over the entire data set? So we have here 5 dots or 5 patients in our data set, and overall we have 8. So in child 1 group, or age less than or equal to 30 group, we have 5 over 8 in terms of proportionality. In child 2, where age is greater than 30, we have 3 instances, 3 records over 8. So that is the actually where we keep the information, how many records we have from that particular category. If you go back to the health case where we have only 2 good health patients, can we make a solid prediction based on that? So we need to consider how many instances we have from a particular group when we think about how much that category can help us to estimate the target variable. So if you put down to this our formulation, we have 5 over 8 cases in the first group times its entropy, 0.97, provided by age feature. So this value by itself doesn't have any unit. We can't currently know whether this is a good value or not. We may know that in the best case, a feature can decrease the entropy to 0. So we can have 0 in here. Like assume that both childs will provide us pure outcome, pure entropy, which is 0. In the best case, this value can be high 0.95, and age actually give us information gain 0.35. But we need to think about other features in our data set to understand whether age is informative enough to include in our model. Okay. So let me check questions, and then we will move to other features. Can we replace child with gender instead of age, right? One question is, so currently we are looking into the age feature only, and in the age feature we have 2 categories, less than or equal to 30, greater than 30. So when we look at gender, then the child will become female, male. In age, it is less than or equal to 30, greater than 30, and in health, child are poor and good. So those child nodes obtained based on the categories in the data. We go feature based, so we start with age. Now we are going to check gender, then we are going to check health. And when we consider a particular feature, we check the categories in that feature. So we can't have child or the age category as female and male. In the age variable, we have less than or equal to 30, greater than 30. We only check its particular categories when we evaluate the entropy of a feature, of a variable. Okay. I hope this is clear. Another question, is the base of logarithm is always 2? Yes, it is always 2. So that if I go back to the entropy calculation, so these 2 here, let me clarify, is not due to the number of classes in the target variable. Logarithm 2 is due to the information theory. So we have, in computer language, we can represent everything in zeros and ones, right? It's binary. So that 2 actually comes based on that theory. So this doesn't mean if we have 3 categories, this will be 3. It will be always 2. If we have 3 categories, then we will continue to add the other outcome. So in the whole formulation, let me go back. This C is the number of categories in the target variable. So here we have yes or no. If we have yes, no, in between, for instance, then we will add the other category here, but it will be always logarithm. Let me check the other questions. Okay. In information gain, like entropy closer to 1, the more relevant, or vice versa. I didn't understand. So what we are trying to do, we would like to see which features provide the highest information gain. So which features can help us to decrease the entropy to the pure case, 0 case. So in age, if you know the age category, let's go to the result here. If we know the age feature in our data set, we can decrease the entropy by 0.35 in the entire data. If we know age, so let me see whether we calculate the whole entropy of age. So for the entropy, one of the categories in the age can help us to have 0 entropy, but in the other category, we have really high entropy. So overall, this value actually 0.60, right? So that we decrease the whole entropy by 0.35. If age has an entropy of 0, that means by knowing the age of the patient, we can actually make solid predictions for the outcome, whether the medicine would be effective or not. But currently, it's not pure. Entropy of age category is 0.6, and it can provide us the information gain of 0.35. So by itself, we can't currently say anything. We need to see how much information gain we will obtain from the gender, how much information gain we are going to obtain from health, so that we know which feature is more informative compared to the rest. Another question, how to interpret the information gain. So I just answered that. We will compare all of the other features and then we will order them. Okay, age is the most informative one and then health is the least informative one. Okay, by itself, we can't say anything. Another question, in a real scenario, we might have a lot of variables. We need to calculate the entropy for all variables? Yes. So luckily, there's a package in Python, also in R. It will automatically calculate the information gain obtained by each feature. And then actually you can use that information to decide which features to use for modeling. So we will take a subset of the features. We are not going to use all of them. We will use subset of the features in model building stage. And how we decide that subset, it will be based on the information gain provided by each feature. Okay. The other questions were similar, how we are going to actually interpret this result. As I mentioned, we need to compare all of them. So let's continue and you will have a better understanding. So by age, we know that age can decrease the entropy by 0.35. So what does this mean? Knowing age, using age information when making a prediction, or using age information of the patient when making a prediction, we can decrease the entropy by itself. We can't make any judgments. We need to see how much we can decrease by knowing other features. So let's do it for gender. What we do, we go to a particular feature, and then in that feature, we check the categories. Based on those categories, we define our child. So here in gender column, we have two childs. One of them is gender female, the other one is gender male. If you check gender female, in gender female, we have two no cases, 2 yes cases. And for gender male, we have 1 no, 3 yes cases. So these trials actually created based on this distribution. So let's make guesses. What is the entropy for gender female? What can you say? Any guesses for female child? Can you guess the entropy? Okay, for female, if you check, we have 2 yes cases, 2 no cases. So it's highly mixed, right? We have 50% from one class and 50% from the other class. So that means entropy is the highest, which is 1. Highly disordered. If you know the gender male, in the gender male category, do you think entropy is close to 1 or close to 0? We can't directly calculate it, but we know we have majority yes cases and only 1 no case. So that means we are almost highly pure. So it is close to 0. Okay. So for female, you have already calculated it. We have 2/4 for yes cases, 2/4 for no cases. So this is highly impure, entropy is 1. When you put down to the formulation, the probabilities are 0.5. So entropy equals to 1. For the male case, what are the probabilities? We have for probability yes, 3/4. And for probability no, we have 1/4. So we will mainly put this down to the formulation. This is 3/4, 0.75, logarithm to 0.75, and for the no outcome, 0.25, logarithm to 0.25. And it is 0.81. I was expecting something quite close to 0, but yeah, logarithm didn't provide us that. Compared to the initial one, it is less disordered, but still it is close to 1. Okay, now how we are going to calculate the entropy. Entropy of the parent is 0.95, which has been already calculated. Now, by knowing the gender information, we have gender female. Overall, here we have 4 cases, right? We have 4 dots. And in our data set, we have 4/8. So we have 8 records or patients. And for the gender male, we have 4/8. So this is the proportion of gender female. And this is the proportion of gender male. Okay, so we calculate check how many records we have in each category. And that is the proportion of child. So it is basically 0.95 minus 4/8 times entropy 1 plus 4/8 times 0.81. And this is the entropy obtained with gender information. And this, as you may remember, entire data set, no information. So when we know the gender of the patient, how much we can decrease the overall entropy? 0.05. So in age, this was 0.35. Now we can make some judgments or we can obtain some insights. By knowing age, we can actually make better predictions compared to by only knowing gender of the patient. By knowing gender, we can actually decrease the entropy by 0.05. By knowing age, we can decrease the whole entropy of the dataset by 0.35. So if you compare two features, age is more informative than gender. by knowing gender, still we can make lots of errors when we predict the outcome, whether the medicine would be effective or not. Okay. Now, let me ask you a question. What is the entropy of knowing health? So let's check the categories in health. We have poor and good, and childs are already here. So can you make a guess? Can you calculate the entropy and information gain by knowing health? Let me give you a few minutes. First of all, let's discuss if you know health good. What is the entropy for health good? Yes, I see lots of correct answers. It is 1, right? We have 3 yes cases, 3 no cases. So these are the actually 2 extreme boundaries. For health good, we have entropy 0. This is pure. Only 2 outcomes, so entropy 0, 2 yes. And this is impure. We have 3 yes cases, 3 no cases, so 50% from each. So that means entropy is 1. So highly mixed. If we consider for the good health, let's calculate this. We already know it is 0, and for pure, it is 1. And now for the information gain, let's do it together here. For the entire data set, it is 0.95 minus check all of them. For age, it is 0.35 information gain. For health, 0.20. For gender, 0.05. So what does it tell us? Age provides the highest information about the target variable, which is medicine would be effective or not. Then past health history, whether the patient has a good health or poor health, knowing this can help us to predict the outcome much better than knowing the gender. So if you order these features, age is more informative, then we have health, then we have gender. Okay. So let me see whether there are any questions. Any questions about this topic before I summarize? So please type your questions and let me just cover again. So information gain will tell us which features are more informative or provide more information about the target variable. So in this case, what we did, we individually check gender, then we check age, health, and try to see, by knowing these features, whether we can make a better prediction about the target variable. For instance, by knowing the ID, we will not make any good prediction, right? It doesn't provide any information about the target. So it is similar. Like if we know the gender of the patient, can we predict whether the medicine would be effective or not? Or if we know the age of the patient, can we predict whether the medicine would be effective or not? Still, we can make errors, but when you compare these features with each other individually, you can actually estimate which ones provide you more information. And when we implement in our workshop next week, you will see that some of the features have an information gain of 0 or very, very close to 0, like in gender. And if you see there's a high jump, so here we see that age and health are quite close to each other, but we don't see a kind of huge jump. In some cases, we may have a feature with information gain with 0.6 and the rest is with 0.002 or 0.01. So when you see high jump, you can actually decide, okay, I am going to only use these features to make a prediction. So this will tell you actually how much those features can help you to have a better prediction compared to the rest. And decision trees actually work based on information gain value. You will kind of connect it better during our workshop next week, since I will continue to discuss decision trees and you will know how they work in general. But before that, let's summarize some of the common feature selection methods. So by the way, feature selection is definitely used. And there are some machine learning techniques. They already have their own feature selection method embedded. They don't use all of the features. They use only informative ones when they make a prediction. So information gain is known as filtering method. So we actually, when we make a decision, we consider each feature individually. So for instance, what we did, we check age. We divide the data set based on age. We didn't consider health and gender. We only checked the relation between age and the target variable. Then when we check health, we only consider health and target variable. When we check gender, we only consider gender and target variable. So there is no cross effect. Each feature considered individually, and this is called filter methods. They are simple. They can be quite efficient, since we don't need to consider rest of the features. But it also has a disadvantage. Since we only consider an individual feature, there is no interaction involved with the rest of the features, and this may actually cause a wrong information, wrong signal. Maybe gender, for instance, if I go back to here, maybe gender by itself is not that much informative, but if we know the gender and health, maybe it is quite good to directly predict whether the medicine would be effective or not. The information gain or chi-square test, they don't consider interactions. In kind of improvement to the filtering methods, now they consider the combinations. So here it's quite easy, right? You consider individually age, health, gender, and then you consider gender, age, gender, health, age, health. And you also consider 3 of them. So the wrapper methods consider all possible combinations. They are more strong than compared to information gain, since they consider all potential combinations, but they are computationally demanding. In this case, we have only few combinations, but in reality, when you have 200 records, considering all possible combinations is not easy to compute. And the third one is embedded methods. So as I mentioned, most machine learning models have their own feature selection, and this can be also used to identify which features are informative or not. So we will see, especially the one by the random forest in the upcoming weeks, we will see embedded methods. You can also use that outcome to filter out some of the features. Okay, so this is the end of this class, and next week we will continue with decision trees and we will see how to implement information gain. So I can take any questions if you have. And okay, let me check the questions. Higher the information gain value, the more informative the attribute. That's correct. If I go back to the previous slide, highest information gain, and that's the actually, if you go back to the formulation, we compare the information, entropy of the parent entire data set. So without any future information, how our data is distributed. This is the entropy of the entire data set. If you don't know any features like age, gender, and health in this case, how is our data actually distributed? High entropy means our data is really, really complex. We have 50% from one class, 50% from the rest of the class, let's say, with high entropy. And then by using the individual features like age, gender, and health separately, we don't consider cross effects, how much we can decrease that entropy. So that's the information gain. How much, by knowing a feature, we can decrease the entropy of the entire data set. And highest information gain means that particular feature can help us to make better predictions. Higher the value, more informative the feature. One question is it possible to calculate the entropy of a combination of features, or we do that when testing the model? Information gain only considered separately, but you can artificially generate combinations of the variables as additional features and then apply information gain. Or as I mentioned, there are wrapper methods which does it automatically. You can use one of the wrapper methods to consider combinations of the features to calculate the information gain. One question, in this case, we will eliminate gender, right? So if we check the comparison, gender has the lowest, but we have, if you check the kind of difference between age and health, we have 0.15, and between health and gender, we have 0.15. So there is no high jump. Currently, we can't directly say not including gender will help. If there's a high jump, we generally kind of cut off from the tail. But always we check what happens when we apply, or when we, let's say, cut off from a particular value and only include one group which has information gain, let's say, higher than 0.20. So we also check how this will affect the performance. And the follow-up question, would we create models for different combinations once we have selected the subset of features to see which combination we get a higher accuracy? We don't do that much calculation actually. So since otherwise, if you have 200 features, combinations and building models for all combinations will take ages. We use indication by the models or these techniques like wrapper methods, information gain, or embedded, let's say, technique from random forest. You use that outcome to decide which features to include. Okay, one question, we will not use the variable with low information gain values when modeling. Yes, so some of them will provide no information at all. We will see during workshop. Mostly we will try to understand the tail and cut off from the tail. So we will exclude those. And one question, any updates on the package installation issue from workshop Wednesday? It was on Tuesday, still working on it. I will post an announcement. Hopefully we will resolve when we resolve it. Okay, yeah, thank you all. And I don't see any. There is one more in real world practices. Do we know when to use different types of selection methods in our prediction model? When to use, sorry, I misread the question. When to use different types of, we always check feature selection methods, since some of the features definitely will will not provide any information about the target variable, and including those actually will affect the performance of the target variable. We generally start by all features, see how our model actually works, and then if we are not happy with the model outcome, like prediction, or if we are suspicious of some problems, we will discuss it in the upcoming weeks. We use feature selection to get rid of the problematic features, and we check how it will help us to improve the model outcome. Okay, thank you all. I can answer a few more questions, but please feel free to leave if you don't have any. What constitutes a high jump? Is it more 0.5 difference between head and tail? So it's better when we actually discuss this over an example, since currently it's not possible to see, but we may have information gain, let's say 0.75, 0.60, and then there is a tail with zero values or very close to zero. So then you can understand the tail. We will visualize this to see the information gain values provided by the rest of the for the all features in our data set, and then that visualization will also help us to see where is the cutoff. Okay, I hope this is clear. And should we always round up to 2 decimal places? This is just for illustration, but are you asking for in general for the exam type of calculations, or in general? Information gain values can be quite close to each other, but we don't just not include a variable if it is only make difference in the 3rd decimal place. We will really look for high jumps when we decide which variables to include in our modeling. I hope this answers your question. For these examples, 2 decimal places would be fine. Okay. Thank you all. I hope this concept is clear to you. When we implement it and when we discuss the decision trees, it will make more sense. And hopefully you will see more examples and you will understand better when we discuss it during our workshops next week. Thank you all. Have a nice weekend, and I will see you on Monday and Tuesday depending on your workshop.